Hello, this is Grace, Aidan, and Sarah, and we are Group 7.1 in the Mechanical Engineering Systems Lab course at Penn State. Over the past several weeks, our group has been working on various tasks to learn and demonstrate the capabilities of autonomous vehicles using a JetBot. A JetBot is a differential drive robot powered by NVIDIA Jetson Nano AI computer and is programmed using Python. With the JetBot, we did 3 different labs as well as a cumulative demonstration, combining different tasks learned from each lab. Today we will be discussing the 3 labs and their contents, as well as our team-defined task and how we used a flowchart to explain this task. We began Lab 1 by analyzing the various parts of our assigned JetBot, JetBot 7. From here, we connected to Jupyter Lab for the first time. Jupyter Lab is the software system that was used throughout this process to control the JetBot. The first step was to familiarize ourselves with the program and important functions such as writing text and starting and stopping the kernel. We then moved into basic motion control. Here are some examples of the left and right motors moving at various speeds. Now that we gained an understanding of the main functions of the JetBot, we needed to calibrate the wheel speed. This was done by doing multiple iterations of setting the JetBot down a straight driveway that was 2 blocks long. We timed this and recorded the distance from the center line for each run to eventually calculate the bias. Finally, we used inverse kinematics to position the JetBot. In this lab, we only moved about a basic 4-way intersection, but this action was crucial as it was a major action that we used throughout our team-defined task.
In the second lab that we did, we focused on path following as well as image processing and image classification. Using a camera sensor to generate heading angles, as seen in the image, these angles act as the input to the control system, which are then sent through a PD controller. The vertical line acts as the center of the JetBot, and we are able to calculate the angle to the target position, or the green dot in the image. These input signals generate an actuating signal, which is sent to the motor wheels to follow a defined path, such as the yellow lines of the road. You can see in this image, view as if they were driving on an actual road, how the camera signals are able to be used to generate and pick up yellow and white lines as seen by the green lines in the image. The second part of this lab involved using the interactive classification tool created by NVIDIA to collect image data and train a learning model to classify different road signs. We took multiple images of the road with different signs such as a stop sign and a speed limit sign. We were able to use the model to accurately predict 3 different conditions successfully, such as no sign at all, a stop sign, and a speed limit sign, as seen in the image, with a probability of over 85%. You can see how in the image the camera is able to pick up the input from the JetBot, and how on the right side with the sliders, when we were able to put signs in front of the camera, the prediction rates were able to move around and indicate to us whether or not it was able to pick up that image. To improve the model, we varied the background of each image as well as the direction of the robot and its camera. As seen in these images, you can see how we varied the angle without any signs, with the stop sign in the road, and with the speed limit sign as well.
In the third lab, we utilized communication between the JetBot and CameraBot. After connecting to the CameraBot, we were able to take pictures of the road map. Once we successfully gained access to the camera, we were able to calibrate the camera using a checkerboard at various orientations. Upon calibration, we determined the CameraBot's camera matrix and distortion coefficient, which we were able to implement into our code. On top of the JetBot is an identifier called an April tag. Using the CameraBot, we were able to take a picture of our JetBot's April tag on the road map. We implemented this image into our code to identify the coordinates of the JetBot. Next, we uploaded an image of the road map to initialize path planning. Using this image, we converted it to a binary map that only shows black and white. The JetBot recognizes that it can only operate on the white areas of this map. Using these coordinates, we input the initial position of the JetBot and chose a coordinate on the map as our final destination. Next, we were able to create an optimized path that is based on the best nodes to go to from the start and finish point. From this optimized path, we were able to obtain the coordinates that correlate to the nodes on the map. Next, Sarah will explain the flowchart that we used to ultimately create our demonstration.
This is our presentation of the flowchart that we created to explain our process for the team-defined task demonstration. The overall goal of the process that was given in our prompts is to make the JetBot travel from location A to B autonomously using the shortest distances. Of all the subprograms that we worked on in Labs 1 through 3, we chose to pursue basic robot control and kinematics, robot networking and communication, position detection using the April tag, and path planning for our task. To view how these subfunctions connect to create the overall goal, we begin by analyzing inputs and outputs of the subfunctions. For robot networking and communication and the position detection using the April tag, we need the JetBot and CameraBot as inputs. The output of the robot networking communication, which is the image detailing locations that is then used as the input for the position detection using the April tags. This will eventually output a position matrix that can be used for both inverse kinematics and path planning. For path planning, you need to use things such as the physical map JPEG converted to pixels, binary occupancy grids, and probabilistic robot map that declares the final path decision, right, left, or straight. Line following, inverse kinematics, and stopping at a stop sign also have inputs and outputs, such as a variety of images that would be necessary if we were trying to achieve the final overall goal. This overall goal can be demonstrated here as we identify the inputs and outputs of the main program. The inputs include the initial position of the JetBot, the initial position of A, initial position of B, distances between A and B, and then the intermediate points, the motor speed, and even the road signs. The output will be the path that has been identified by the map, the April tag, and point distances that the robot follows to travel from point A to point B. Lastly, you can see this all come together in our flowchart. Our flowchart specifically emphasizes the subfunctions that our group chose to focus on. You begin with the inputs of the different bots, leading to the networking communication subfunction, as well as the output there being that image with the locations. The position detection using the April tag is another subfunction that happens consequently, with several outputs that can also be used as inputs for the path planning. These include that initial position matrix, binary occupancy grid, probabilistic robot map, and physical map with the JPEG converted into pixels, all of these working together for the path planning subfunction to create the path decision, which will be the left, right, or straight. And then a few more things have to happen, such as adjusting the motor speed, identifying the start and end locations before we can move into that basic robot control and kinematics for the end. So these things together will kind of go through the tasks that we've chosen for our demonstration. And in the following section, we will go ahead and show the video of this demonstration.
In conclusion, our team successfully completed the task utilizing 4 out of the 6 objectives. The objectives that we utilized were basic robot control and kinematics, robot networking and communication, position detection using April tag, and path planning. Although we used objectives across all 3 labs, we predominantly used material that was covered in Labs 1 and 3 to complete our demonstration. Thank you for watching.